All right. Blood pressure is not a discrete variable. It's a numerical variable. You may think it's a discrete variable because normally you would say blood pressure is 90 or blood pressure is 85. But really, when you're reading a scale, if you're reading the mercury gauge, right? Or if it's got a dial on, the spring-loaded ones have dials on them or something like that. Really what you're reading, if you look closely enough, it's 98, it's 95.192 or something like that, right? But you just say 95. But it's a continuous scale, right? There's no, in other words, it could be 95, it could be 96, it could be 95.5, it could be 95.55, it could be 95.5555, right? So it's a continuous scale or numerical or scalar or whichever one of those description that you'd want to use for it. Okay, it's not really discrete, even though usually you use an integer number to describe it. It's really continuous. And we're dealing with numerical or continuous variables whenever we do this kind of work with this normal distribution for the time being. We're going to be talking a little bit later about binomial distributions, which are a little bit different. Okay, so at any rate, so this sigma, this standard deviation, represents the spread. And we have something called the empirical rule. Well, the empirical rule tells us that there's something that all of these normal distributions have in common, no matter what the mean is and what the standard deviation is. Let's say I had another standard deviation that had the same mean, and the mean was 100, right? Except this one, the standard deviation is equal to 5. What would that look like? Well, the mean's in the same place, but it's going to be narrower, right? And what if I had the same distribution with a same mean is 100, right? This one's 100 also. But this time the standard deviation is equal to 20. Well, that's going to look wider, something like that, let's say, right? Means in the same spot. Those are all normal distributions. Now, the empirical rule tells us certain things that each one of these distributions has in common because they're all standard, they're all normal distributions. For starters, it tells us that if you're one standard deviation below the mean and one standard deviation above the mean, right? This is one standard deviation below. I'm going to call it -1. This is one standard deviation, and I'm going to call it +1. What's the actual value there for blood pressure? One standard deviation below. What's the standard deviation? 10, right? So if the mean is 100, what is this? It's one standard deviation below. It's 90, right? And what is one standard deviation above? It's a blood pressure of 110, right? Well, if you're between one standard deviation below and one standard deviation above, in this particular case, 90 and 110, the area in here is 68%, right? So now think about this tool. If I told you that the mean is 100 and the standard deviation is 10, now you could just echo back to me, oh, that means people between 90 and 110. That represents 68% of the population. Or I would have a 68% chance of randomly picking someone that's between blood pressure between 90 and 110 from this particular population. Thank you, Katie and Manu. Okay, so at any rate, so now the next thing I know about this is that if I go down to 2 standard deviations below and 2 standard deviations above, right? What would those values be? Be 80, right? And 120. And what percentage of the population is represented here? Anyone has a guess, or maybe you read it from the chapter? Yeah, 95%. Right? Let me ask you a little tricky question now. What percentage of this population would have a blood pressure below 80? Remember, there's area. These are all areas. This is 95% between these two. Exactly, 2.5. And how do we get that 2.5%? Well, we know that if this represents 95% is between 80 and 120, that leaves 5%. We know that this distribution is symmetrical. So if it's symmetrical, the bottom left over here must be 2.5%, and the top left over, or we like to call it tail, must be 2.5%. That's going to be really important. You're going to be listening to us talk about these tails forever, in this amount, at least for another 7 weeks, 6 weeks, or 6.5 weeks, or whatever we have left, or 6 weeks, I guess we have left after tonight, believe it or not. right? So at any rate, so we're not going to know each other for too long. These summer sessions, they really fly by. So at any rate, so that's 2.5%. Well, that's very interesting. But the real power of this is it's universal. Any other normal distribution. Let's say that we looked at BMI, and that's normally, and it happens to be. I don't know if it is or not. I'm going to assume it is for a second. And the mean BMI for a population is 25, and the standard the standard deviation is 3. Let's say. What does that tell us? That tells us that 68% of the population of this population has a BMI between 22, one standard deviation below, and 28, one standard deviation above. Okay, and what percentage of this population has a BMI below 22, less than 22, one standard deviation below? Well, how much of it were you accounted for here with 68%? What's left? 32%. So it's symmetrical. So how much must be below 22 and how much must be above 28? 16%. Each one of these tails is 16%. And again, we could do the same thing with 95%. And finally, 3 standard deviations below and 3 standard deviations above represents 99.7% of the population, right? Basically, almost all of the population. It's unusual to have a normal distribution, have a population where you have people that are outside of 3 standard deviations from the mean. Those are kind of like outliers. Those are people at really unusual values. Okay, and the same thing would happen for any shape or any standard deviation that we would want to use. So we have a document here that I want to open up. Okay, well, first of all, let me just show you this number, this equation. Oops, that's the one I want to show you. Here we go. That formula represents that normal distribution curve. That represents the how high that line is at any given point. This is all based on chance, right? Probability and chance comes up with this formula, and that represents the shape of that normal distribution. As you go further to, as x goes further to the right, gets below, x is below. There's x and mu is in there, right? The particular value and the mean are in there somewhere along with the standard deviation. As you go from way below the mean for x to way above the mean for x, that line goes up, that f of x, that value, that y value goes up, peaks, and then comes down again, right? So it gives us that bell-shaped curve. That formula represents that line. And since we have a formula that represents that line, it's possible for us to use that formula to calculate all the other points that we don't have in the empirical rule. In other words, it was very nice that I told you what would happen at 1 standard deviation below or 2 standard deviations above. But what about if we're dealing with a value that's 1.5 standard deviations above or 1.5 standard deviations below, or 2.3 standard deviations above or below? Well, we need a mechanism. We may need a mechanism to figure out what those areas of that curve of that distribution are, and that having this formula, the fact that this is all based on this formula, allows us to do it. Does it look like we're really going to use that formula to do this? Not likely, right? We have tables that represent all these values, right? Okay, so first of all, yes. Yeah, that's E. It's a natural. That's E, the natural number E for logarithms, natural logarithms, E. Okay, so at any rate, so I think the value is like 2.71 something or other, kind of like pi. It's a continuous number. So at any rate, so we're not going to use that anyway. So we're not going to have to worry about that. Maybe if you take an advanced course or something like that. I think most people take PH750. This is basically it for you guys, right? You don't take another statistics course. You take EPI, but you don't take another statistics course. I think people that take 751 wind up then going into some of the other statistic courses. So they may actually have to, learn a little bit of that stuff, so, or be tortured by it, one or the other. So at any rate, so now let's take a look at this. So now that means we may be able to use that formula, apply that formula, help us out with some of this stuff. So let's try a few exercises based on this. And I have a document that's on Blackboard which is called, I think, a summer to 2015 session 4 lab, so on and so forth. And if you open that up, you'll be able to take a look at this. Let's see. I think there was a question I missed because somebody answered it for me online. Yeah, let me show you that. Here's the chart right here. This is the empirical rule. You're looking at it right now. Let's see if we can blow this up a little. There you go. Here is the empirical rule. That's in your textbook, and it's in many textbooks. You can look it up on the internet and confirm the fact that I did not make any of this stuff up. This version of it is a little bit more precise. Remember, all of this empirical rule is an estimate. It's not exactly right, right? But if we want a really exact number, we need to use that formula or use Excel, which has functions based on that formula, or use a table, which is based on that formula. We're going to use the table most of the time. So at any rate, so you can see that really in this form of it, they say really the 1 standard deviation below to 1 standard deviation above is really 68. Is a better estimate would be 68.2% rather than 68%, and so on and so forth. But I wouldn't worry about that too much. Well, they call it 68% too over here. But I wouldn't worry about that too much right now. This empirical rule is really meant as an estimate. Now, this number of standard deviations below and above the mean, a lot of times we're going to want to give it a shortcut name. And we're going to call the number of standard deviations below the mean and above the mean, we're going to call that a z-score. Okay, so from now on, if you hear the term z-score, it refers to how many standard deviations below the mean or above the mean that a particular value is. So if I tell you that the z-score is minus something, is it below the mean or above the mean? Below the mean, right? If it's a plus, it's above the mean, right? And how am I going to calculate that? Well, one of the ways you can calculate it is just by using a simple formula like something like this. Okay, if I were going to take a number like 105, and I asked you, what's that value? What is the z-score for 105 in this distribution where 100 is the mean and 10 is the standard deviation? Well, it's the number of standard deviations above the mean. Well, this is 5 above 100, and the standard deviation is 10. So I know using my noodle that that's a z-score of plus 1/2. It's half of a standard deviation above the mean. If you don't want to do it that way, you can say to yourself, well, the z-score is equal to whatever x is, whatever that value is, minus the mean over the standard deviation. So if I do it this way, you'll see 105 minus 100. That's just simply the difference between that value and the mean, divided by the standard deviation was 10, and that's going to be equal to 5 over 10, or 0.5. Right? That's a z-score of plus 0.5. If I had done the same thing for a value of 85, how would that have worked out? It would have been 85 minus 100 over 10, right? That would be minus 15 over 10, which would be minus 1.5, a z-score of minus 1.5. See, so naturally, if you use that formula, it'll work out the positives and the negatives because 85 is to the left of the mean and 105 is to the right of the mean. So from now on, z-score is a number of standard deviations. That's really what it boils down to. That's really all that is. Okay, so now let's go back and take a look at our empirical formula. Let's give this a little bit of a workout here. Now, I like to always draw the distribution out because it makes it less likely that I'm going to make a mistake. Okay, and makes the whole thing a little bit more intuitive. We just went over that. So I have a blank version of this here. So let me see what I can get here. Assume that the heights of adult Caucasian men have a mean of 68 inches and a standard deviation of 4 inches. And assume that these are normal distributions. Find the probability that a randomly chosen individual from this population has a height greater than 68, between 64 and 72, between 60 and 76. So what I'm going to do is I'm going to move this over. I'm going to reduce the size of this. I don't like doing it, but I want to get both of these on here at the same time. Oops. Okay. Narrow that out a little bit. Pull this back. Try this again. Okay, and here's our distribution. I want to make sure that everybody's muted here again, too. Okay, so make this a little smaller. Okay, I think I can work with both of these at the same time. Okay, where's my first example there? Okay, the heights of adult Caucasian men is mean is 68 inches. Okay, so the mean is 68. Right, that's our mean. Standard deviation of 4 inches. Sigma is equal to 4. Okay, find the probability to randomly choose an individual from this population at a height greater than 68 inches. What's the probability their height's greater than 68 inches? 50%, right? 68 is the mean. So what's the z-score of 68? 0, right? 68 minus 68 is 0. Okay, so that's 50. That the answer to our first part is 50. Is 50%. Probability that a randomly chosen individual will be between 64 and 72 inches. 64 and 72 inches. What's the probability that they'll fall in that range if you randomly choose someone? How many standard deviations below is this? 1 and 1 above. So what's the area in there? 68%. Good, guys at home are getting this too. Okay, good. What's the probability that it's between 60 and 76 inches? Okay, that's 2 standard deviations below and 2 standard deviations above now. So that's going to be 95%, right? Probability that you're going to choose someone that's within between 60 and 6, whatever that was, 60 and 72. Was that what I said? No, 76 is 95%. Okay, let's try next one. Assume that the heights of adult Caucasian women have a mean of 63 and a standard deviation of 3. What percentage of this population have a mean height greater than 63? We just did that before, right? Same thing, 50% greater than 66 inches. Up, a little bit of a curveball there, right? Let's go get another chart here. Okay, let me make this a little narrower. We're going to work with both pages at the same time. Yeah. Okay. Okay, what I say the mean was for these women? 63. Mean is 63, and the standard deviation is 3. Okay, 50 at 63, 50% for the first question, greater than 66 inches. What's the probability that we'll pick someone out at random that's greater than 66 inches? That's that end of that's that tail, right? So what's the area between 1 standard deviation below and 1 standard deviation above? That's 68%, correct? Okay, so that means that this part is 34 and this part is 34. So if everything above the mean is 50% and 34% of it is below the 66, what does that leave above the 66? 16%. Okay, so see how much we know about this population just from those two numbers, mean and standard deviation? And this is true over and over again for all these other populations. The next one was less than 60 inches. Well, less than 60 inches, we're doing basically the same thing, aren't we? We're talking about this area here, and we know that this is 34, so this also has to be 16, because to the left of the mean is going to be 50% of the distribution also. Okay, there's a lot of ways you can work this around. The gestation time for humans has a mean of 266 days with a standard deviation of 25. What percentage of pregnancies would you expect to be greater than 291 days? Let me get a brand new, you know what I'm going to try so I can't. It's going to take me forever to back through these. Okay, I'm just going to switch my page. And we get a fresh graph. Now, a lot of you guys are saying, oh, it's pretty simple now with this empirical formula stuff. I don't need to draw the graph, and that's probably going to be true in a lot of cases. I like to do it just to make sure, especially on an exam or something like that, or homework. So, when you have the time to do it, it might make it a little easier to make sure you get the thing right. Okay, so the mean is 266. The standard deviation is 25. Okay, what percentage of pregnancy would you expect to be greater than 291 days? Okay, say 291 is up here somewhere. I don't know where it's going to be. How am I going to figure out a z-score for this? Right, this is a little bit, it's not even numbers. I'm not a real smart guy. So to make sure I don't make a mistake, I'm going to use the formula. Z is equal to x, the value I'm interested in is 291, minus the mean, 266, over the standard deviation, which is 25. As it happens, this winds up being 25 over 25 and a z-score of +1. So that area, again, is about 16%, right? What's the next one? Less than 241 days. Okay, 241 minus 266. Again, this is 25. That's a -1. So it's basically the same as before, 16%. Less than 241 days or greater than 291. Oh, wow, this is great. I love this. This is terrific. The guys here in the lab here are much smarter than the people at home, I think. Because they got the answer right. Oh, a couple of them got the answer too. All right. Well, maybe I was wrong. All right. So at any rate, yeah, 32% because that's what is that when we talk about that in terms of Venn diagrams? That was a union. It could be either case satisfies it. So it's 16 plus 16. We add them together. 16% chance for below 241 and a 16% chance for above 291. So overall, we have a 32% chance of getting we have a 32% chance of getting a value that's either below 241 or above 291. Okay, so it's double. Does that make sense, DJ? Because we double the chances because we said we would be satisfied with it being less than 241, 16% chance of that, or greater than 291. So we're happy with both of those outcomes. So we actually include the probability for both of those outcomes. Okay, so, let's see if we can do some more of these. Yes? So, number 3. Yes. Yes. What was the answer? Number 3 was that was a z-score of -1 and +1, right? Or +1 and -1 actually. No, in fact, that's one of the things Levi was talking about in the lecture. See the way that this tails off? This is what they call asymptotic. It never goes to zero. The net probability never goes to zero. In other words, it's possible somebody could have a blood pressure of 30, right? But that might be like, that might only occur one in a million, 1 in 10 million. So as you get further and further away, the higher and higher lower and lower, more and more standard deviations away from the mean. Thank you for the help, by the way, online. I like the fact you guys online are discussing these while I don't have a chance to direct my attention over there. So keep doing that. So at any rate, the further away you get from the mean, the less likely you're going to get that outcome. You guys were reading about this particle accelerator in Zurn in Switzerland, where they're trying to prove that this Bose, what is it called? Yeah. Right. Yeah. What was it again? Bose Hickson particle exists. It accounts for like it accounts for gravity basically. Like the functional part, the functional thing that creates gravity, right? So they've been debating whether this thing exists or not, and they've been doing calculations, and a lot of the calculations because they do a test, and sometimes they get one answer, sometimes they get another answer, right? They've been using statistical analyses to determine what's the likelihood that they have really discovered the Bose-Higgs, whatever it is, boson. Boson? Higgs boson. Higgs boson. Okay, good. Thank you. What is the probability that this data really shows that they've discovered the thing? Well, they run so many tests and do so many analysis, they want to really be sure. the standard that they're now well, you guys, most of the time when you read a study, what's the level of acceptable error? They call it alpha error in most sociological studies or public health studies and so on and so forth. You ever notice what's the probability? What's the chance of making an error that they find acceptable? Yeah, well, usually 5%. Usually an alpha error 5%. That means you could be, like if you're drawing the wrong conclusions 5% of the time, right? So now in this analysis that these physicists are doing, their acceptable level of being wrong is they want to be able to be certain that they found this thing to 6 standard deviations, right? So their level of acceptable error is far, less than in typical studies that we would be doing. But that puts kind of into perspective that this normal distribution is really asymptotic. It really doesn't go to zero. Practical basis, it does go to zero because you can't have below zero blood pressure, right? Or unless you're a vampire, right? Because vampires have below zero, right? Never mind. I'm sorry I brought that up. So at any rate, assume okay, we got heights. I'm going to skip over to this body temperature one. Body temperature of adults have a mean of 98.6 degrees with a standard deviation of 0.6 degrees Fahrenheit. Find the probability that a randomly selected individual has a body temperature that is greater than 99 degrees Fahrenheit. Well, I'm gonna go over here and I'm gonna actually kind of move over to the right here. And I'm going to write this down here. Okay, and I'm not going to, for the moment here, I'm not going to draw this. I'm going to say that the mean is equal to 98.6. And the standard deviation is equal to 0.60. Okay, and I want to know what's the probability that we have a temperature that's greater than 99 degrees. Okay, well now what's the z-score for that? See, if I drew a normal distribution, that would be 98.6. Okay, and this would be 99, and that would be less than 1 z-score, right? Well, what is it? Z is equal to 99 minus 98.6 over 0.6. So that Z is equal to 0.4 over 0.6, which is, I'm going to round it to 0.67. So it's got a z-score of plus 0.67. It's not a whole number. What am I going to do now? I can't really apply my empirical rule, right? In fact, my empirical rule might be nice anyway because I can say what are they asking above, greater than that number. Okay, I could say, well, see if it were 1, this would be 16, right? If it were 0 z-score, it would be 50%. So it's somewhere, this area to the right here is somewhere between 16 and 50%. Maybe it's 20% or 30%. So I can use the empirical formula to kind of get a look at what it might be. But I want to know more precisely, what is this area to the right of 99 degrees that has a z-score of plus 0.67? Now is where we're going to apply that formula, which describes the normal distribution. And we're going to apply it from a table. Okay, so I'm going to open up a table here, which is you can have it on Blackboard, you can have it in your manual, and so on and so forth. I'm going to show you a couple of different versions of it. This one is from a textbook we use occasionally called Agrestes. Okay, I think it's statistical interpreting data, statistical data, or something like that. I forget the exact title of the book, but the author's name is Agrestes. So I'm looking at this, and I see a column here. It's kind of yellowed out a little bit called Z. So that's the z-score here. These are all negative z-scores. These are all positive z-scores. The reason why this table has negative and positive z-scores is it actually shows you up here the area that's represented by the z-score that it's describing. So on this first table with the negative z-score, the area it's describing is the area to the left of that negative z-score, the area that's discolored. Okay, and as I go to the next page, you'll notice that it starts with all positive z-scores. It starts with a z-score of 0, and they're all positive z-scores. but it still is describing the area to the left of that z-score. In this case, the z's are always above 0. They're always positive numbers, and so that the area to the left of that z-score is always more than 50%. On the first table, it's always less than 50% because it's to the left of the mean, and on the second table. So now this is the idea that Levi was telling us about and warning us about, that a lot of these tables, they work this different ways. They'll describe an area to the right tail, to the right of the z-score, and so this particular table, it always gives us an area to the left. So what was the z-score we just talked about? It was 0.67, a positive number, right? Okay, so this is a z-score of 0. This is a z-score of 1. Here's a z-score of 0.6, right? Well, we want 0.67. So in order to be able to calculate more numbers, we have to go across to represent, to get that third digit. 0.0601234567. Yeah, and you guys online are even getting ahead of me a little bit, right? Okay, so the area that's represented to the left of that z-score of 0.67 is 74.54%, or 0.7454, right? Did I get it wrong? Did I move? Yes, 0.7486. Excuse me. Yeah, I was glancing over at the questions and stuff like that. That sounds like a good excuse, right? Okay, good. Okay, so points. I'm gonna round that off because I'll never remember all those numbers. I'm gonna call it 0.75. Okay, so at any rate, so what percentage is greater than 99? Is the 0.75? No, that's to the right. We want to know what's to the left. So it's actually 0.25 or 25%, or really 25.14% or 0.2514. Whatever was the difference from 100% would be the percentage of people that we would expect to have a temperature above 99 degrees. Less than 98 degrees. Oh, okay. Now we're less than 98 degrees. That's 0.6 of a degree, right? Below the mean, and we know that standard deviation is 0.6. So just in our heads, we can tell that's a z-score of -1. So we could use the empirical formula. Let's see what it looks like. If we use the empirical formula, we say it has a z-score of 1, and we've already done this a few times. We know the area to the left of that should be around 16%, right? We've done that already. Okay, so now I'm going to do it with the table instead. So it's a negative 1.0. So a z-score of negative 1.00 represents an area to the left of not 16%, but 15.87 or 0.1587, right? Not exactly, so this is exact, right? Where the empirical formula was kind of an estimate. Okay, so makes sense? So let me step back for a second. How many of you don't feel comfortable with this so far? Okay, you still haven't, we have just that last bit? Oh, with the table part. Okay, we're going to get more exercise. Yeah, we're going to get some more exercise with the table. Everybody on the side's okay. All right, how about you guys online? How are you guys doing? So that's the probability. That could be looked at two ways, right? That's the percentage of people in the population that have temperature below 98, or it could be looked at as the probability that if you picked one random person from that population, they would have a temperature less than 98 degrees. You could look at it both ways. I'm going to show you that we're going to do another example with the table, and this time I'll make sure that I draw it on the graph also, because I think not drawing that on the graph, I think made it a little bit more confusing. Okay, so let's try the next one. Okay, percentage of school teachers in the United States. I guess let me rephrase that. The elementary school teachers in the United States have a mean of $32,000 and a standard deviation of $3,000. What percentage of teachers would you expect to have a salary greater than $36,500? Okay, so let's draw that actually, rather than just kind of wing it. So the mean, okay, I'm going to ask you guys to help me out with this so that I get this right. The mean was $36,500. 36,500 was the mean. 33,000. See, I got a 32. 32, I got it wrong already. And the standard deviation was how much? Yeah, 3,000. Okay, it's 3,000. Okay, and we want to know what's the probability of having a salary greater than $36,500, which is the same thing as saying what percentage of teachers in the population have a salary of greater than 36,500. Because if 10% of them have a salary greater than that, the probability of picking one person and them having a salary greater than that would be 10%, obviously. Okay, so maybe not obviously, but take my word for it. Okay, so $36,500. So this would be, we're going to be up here somewhere. $36,500. So what is the z-score for $36,500? So z is equal to x minus mu over sigma, which is equal to 36,500 minus 32,500 over 3,000. And what does that come out to? Was that 4,000? 30, what was it? It was 32,000. Yeah, 32,000. And 36,500. I wish I had written this more neatly. Minus 32,000. 32,000. So what is that? That's 4,500. 4,500. Come on, 4,500 over 3,000. So what is the z-score for 36,500? It's plus 1.5. Okay, so let's find what area. Now remember, our table is going to give, if I look up a z-score of plus 1.5, it's going to give me the area to the right of this. The problem is asking it's a percentage with respect to a salary greater than this. So we're actually interested in this area here, but our table is going to give us this area here. So we're going to have to subtract it from 100% or from 1, depending on if we're describing it as a percentage or a probability. So let's go to our table. We're going to look up a z-score of 1.5. Z-score, it's going to be on the second page. Z-score of 0, Z-score of 1, Z-score of 1.50 is 92.9332. 0.9332. 0.9332. 93.3% of the population of these teachers has a salary below $36,500. So what percent of a salary above that? It's going to be 1 minus 0.9332, or roughly, what is that going to be? 0.678 or something like that. 668, something like that. So this is going to be up 0.0678, 6%, 6.75% roughly. Okay, yes. On this particular table, yes. I'm sorry, no. It's talking about the percentage to, if you're looking at the Z table, it's talking about the percentage to the left.
Whether it's plus or minus,
it's always, yeah, take a look here. If you look at this, because you're dealing with negative numbers, see, when you're dealing with to the left of the mean, it's all negative numbers. And if you look, all of these numbers, see any of these numbers, none of them go above 50%. So they're all to the left of the mean. None of them get bigger than 50%. Because even at 0, 0, it's 50%. When the mean is 0, it's 50. And this one picks up from there and continues to the right. So all of these values are above 50%. If you look at the table, all of those are above 50%, because since the z-score is positive, it represents areas that to the right of that z-score are always going to be more than 50%, because they're to the right of the mean.
that makes sense. But then, how did you know 93% of the population salary is below that?
Well, because we looked at the number 36,500, right? That number is way above the mean, right? So I know that that more than 50% of the teachers are going to be below that value, going to have salaries below that value, right? Because it's above the mean, right? If you were making the mean salary, half the teachers would be making less than you, half would be making more than you. Since you're above the mean, more than half the teachers, more than 50% of the teachers are going to be making less than you. Okay, so I use my table to figure out what that area is. And you can see, because we're so far to the right, it's going to be a lot of teachers are making less than you, right? So if I use the table here and I use the positive numbers, 1.5, it shows me that that area to the left of that value is like 93% of the teachers. That leaves 7% of the teachers making more than that value to that side. So it just happened the question could have asked what percentage of teachers are making less than that value, in which case the answer would have been 93%. Less than 20, I think that means 28,000. I don't think they mean 28,000. I don't think I meant 28,000. Okay, so let's do it for 28,000. Okay, so for 28,000, Z is going to be equal to 28,000 minus 32,000 over 3,000. Okay, which is 4,000 over 3,000, right? Except that it's not just 4,000, it's minus 4,000 over 3,000, which is minus 1.33, right? Okay, look good. So I'm going to go over here, and what are we looking for? What was the question again? It's always good to check the question out before you try and answer it. Find the percentage you expect to have a salary less than 28,000. Okay, so below that z-score of 1.33. So that z-score of 1.33 is going to be all the way over here, right? And we want to know what percentage is below that, right? So I'm going to go here to look up a z-score of negative 1.33, or if I can find my chart again, negative 1.33, negative 1.30. Oops, I'm on the wrong side, right? Okay, good. Thanks for reminding me that. Okay, I had some shutters here. Negative 1.330, 1.30, right? So to the left of that is about 9%, 9.18 or 0.0918. Okay, this would be 0.0918. And since the table has already given us the area that they're asking for in the question, I don't have to worry about subtracting it from anything or anything like that. Does that help back there? Is that helping you in terms of like the table? Is it a little bit clearer now? Not that last one. Well, we know it's a small percentage, right? Because this is 32,000, right? This is 28,000, salary of 28,000, right? Okay, so that has a z-score of negative 1.3, right? That's our z-score. It's 1.3 standard deviations to the left of the mean. So the question is, what percentage of the teachers have a, what, yeah, well, what I did was I went over here to negative 1.3, but I want, it was negative 1. I'm sorry, it was negative 1.33, right? Negative 1 1/3, 1.33. So I negative 1.3, and remember that like in order to show you the values between negative 1.2 and negative 1.3, it actually lists them across rather than up and down. Otherwise, this table would be like a mile long. So if you look at the top, this represents, each column represents the next digit. So negative 1.30 would have been 9.68%. Negative 1.31 would have been 9.51, negative, and so on and so forth. And negative 1.33, 1 1/3, would be 0.0918, 9.18%. Okay, so that's really just, it's basically applying the table. And really, I should have made this clearer over here. This was negative 1.33, right? It was 4,000 over 3,000, wherever that went to. Wherever, here it is right here, negative 1.3. That's the z-score I was dealing with. Okay, now you got to be a little bit careful because you're going to run across other z-tables in your life as a statistician. For instance, let me see what this one looks like. Take a look at this one. This one gives you the area to the right of the z-score, right? Yes? Is it hard to see? Is that it? Or yeah, yeah, exactly. Right? That's going to give you the area to the right. So you'll notice that all of these start, the mean is 50%. It gives you the area and notice it's only positive numbers, right? It's only positive numbers. So it's giving you the area from the mean, which is 0, to the right. So if I were to look up a z-score of 1, it's 16%. That would be telling us that one standard deviation to the right of the mean, the area to the right of that is about 16%, just as the empirical rule told us, right? So now what if I wanted to know what the area below that is? I'd have to subtract 1 from that. What if I wanted to know for the z-score for the value, the area for z-score of -1? Well, I can't get -1 from this. I can get +1 and find out that this is 15 point, what was it? This was 15.9%, this area, right? But if I have a -1 z-score, well, since this is symmetrical, then that area to the left of a -1 is going to be 15.9% also. Yes. Yep. It's the problem. It can represent either the entire population, represent 100% of the population, or it can represent 100% of the possible outcomes of a random sample, right? So always equal to 1 or 100%. Okay.
The value that they're giving you is X value, and you draw it, draw it as a like alongside the mean, and then from there, based on whatever this value is, like put it in.
Yeah, sure. Why not? I would do. That's exactly what I'm suggesting you do with that. Every time you have a problem like this, you make a little sketch with a normal distribution.
And then depending on what the chart is like, then you know whether it's
Well,
weighted into right or
like for instance, if you use this table and you forgot about that, if you were looking for the area to the left of a standard deviation of 1, right? If you're looking for the area of standard deviation to the left of a standard deviation of +1, you know that's going to be more than 50%. But if you use this table and you look over here and it comes out to be 16% or 15.9% or whatever, and you say, oh, that must be the answer, you realize, oh, it can't be the answer. It's less than 15%. The area I want is the part to the left, which is more. You know you're making a mistake, right? So it always helps to draw it because, especially if we give you some, obviously these are still fairly simple examples, even though we're starting to get a little bit more complicated as we go along. But as we move on with this, you'll see that like sketching it out is not going to take that much more time, and it'll really avoid getting confused with these tables, especially because, like as I said, a lot of these Z tables look kind of. Now, both of these Z tables are on Blackboard. You can download these and keep them for yourself. Take them for posterity. I don't think Agresty's going to be worried about you stealing his Z table, right? And I like that Z table because it's so easy and quick to use because it's a 2-page version and it's hard to make a mistake with that one because you already have the negative and the positive Z scores on there, right? So I like that particular one. That's my favorite. But if you like the Pagano one, you can use that. If you like the one that's in our textbook, you can use that instead. So what I would consider doing is since these are always going to be available to you, like for homework or even on a test, you'll be able to use whichever one you want. I would try and get used to using one of them, get comfortable with one of them, and try and stick with that one, so that when you get to a test or something like that, you don't have to worry about this at all. So okay, let me see what else we got here. Okay, yeah, use whichever table you want. But I think I put all of them up there. Okay, so now just so you know,